Okay, I don't have really a lot of interaction with Dan, but every time we met, it's a very pleasant to listen to his interesting talks and also many enjoyable time. And in particular today, not me, but my joint work. My talk is my collaborator, Hwang To. And I guess he did his postdoc after his graduation in Michigan then. Okay. Okay, so not student, but after he graduated, his first job is at Michigan, and he learned certainly a lot from. Okay. So now the topic today is complex hyperbolic manifold. So let me recall what this was. So here we look at the ball. Unit ball in n-dimensional complex space. And then we are interested in the subgroup, discrete subgroup of the automorphism group of En. And the subgroup we are interested in is we want to look at the compact quotient of the ball. So the subgroup is torsion-free, so it's smooth compact quotient, and discrete, co-compact. And the quotient of ball by such group is called the complex hyperbolic manifold. So this is very interesting object to study from many different directions in mathematics. And this is called hyperbolic because it has hyperbolic metric. Given by this derivative of log, which is the Bergman metric on the ball, and this is invariant on the group, so this descends to a Kähler metric. Omega x on x. So it has locally, it has a hyperbolic metric. Okay. Now let's use this notation. By dBn, I denote by dBn the distance function on Bn. So, and the dx is the distance function on x with respect to these metrics. Okay. Now let's define the following invariant, which is one of the basic invariant of this hyperbolic geometry. So the injectivity radius of gamma, or sometimes or x, is, this is defined as the half of the minimum. Let me first just write the definition. So that's the definition of injectivity radius. And this is geometrically, this is 2 times over rho x is what's called systole over x. And this systole means that this is the length of shortest closed geodesic on X. So in picture, the compact quotients, I mean, in one-dimensional case, it's just Riemann surface. So you can imagine that in higher dimension is some analog of picture like this. Okay, so that's X. And you look at the geodesic, and the shortest closed geodesic. So here, for example, something like this guy. So the length of this is the systole of X. So this is 2 log X. So that's the concept, geometric definition of meaning of injectivity radius. And the systole, if you still haven't heard about this, systole is actually medical term, which is the state of your heart when it is shrunk most. So the highest of your blood pressure is called systole. So if you ever go to a doctor's office and measure your blood pressure, then there's a sign of like systole, and the other one I forgot. But so that's the highest blood pressure of this guy, this manifold, and it's an important invariant of this metric. Okay. And this, of course, this means that for all r smaller than log X, and for any point on the hyperbolic manifold, there exists injective ball Pxr of radius r centered at X. So at any point here, if you choose any point, you can always find an injective ball completely inside here without overlapping, so that the radius is r. So that's another geometric meaning of injectivity radius. So these are certainly, I mean, this is an object, maybe originally arising maybe from group theory or topology, but also differential geometrically very interesting. So, I mean, there are many areas concerned with this object. But today, my interest is the algebraic geometric side of this guy. Now, so far, there's nothing algebraic here. This is a very transcendental object. It's defined by ball inside Cn and then compact quotients. But this turns out to be algebraic variety, as is well known. And this is, of course, the famous result of Kodaira. So let's recall this. So whenever we want to relate such a differential geometric or complex analytic object to algebraic geometry, one of the most efficient way of relating algebraic geometry to such complex analysis or differential geometry is by a numerical condition on the cohomology. This is sometimes called numerical geometry on H1, the Durham cohomology of X. So here, X is no longer hyperbolic manifold, but for X is just any compact scalar. And there's notion of numerical geometry. Now it's rather fashionable. By doing certain numerical study on this cohomology group, you can derive a conclusion about its algebraic geometry. And usually, you can use complex analysis to study such object, such condition. And the prototype of this is, of course, Kodaira's embedding theorem. So let's recall what this was. So we say that a cohomology class, this is positive if it is represented by positive 1-1 form. namely a Kähler form. Now, a line bundle L on X is positive if its Chern class as a class in here is positive. So this is in this, I mean, as it says, it's a numerical condition on the cohomology class. And such a condition is usually easy to check. That's the advantage. And then the Kodaira's embedding theorem says that if L is positive, on X, compact Kähler, then there exists some positive number such that integer, okay, so K is a natural number, such that L tensor K is very ample. So very ample means that, i.e., the sections, holomorphic sections of L tensor K defines a holomorphic embedding of X into the dual of these sections. So X becomes a projective submanifold. So in particular, X is algebraic variety. So it's defined by zero set of some equation, explicit homogeneous equation. So that's Kodaira embedding theorem. And now we can apply this to the hyperbolic manifold. And in fact, this is one of the initial motivation for proving something like this. Kodaira proved this to say something like this. So this corollary is that En mod gamma is projective algebraic variety because the canonical bundle is positive. So in particular, some power of canonical bundle is very ample. So that's Kodaira's theorem. So this object, this complex hyperbolic manifold, turns out to be an algebraic geometric object. So it's an interesting object to study from algebraic geometric point of view. Now, the first question one can ask is to make this embedding more explicit. So you like to really write down this as an algebraic variety. So how to write it down explicitly? That's not easy. And the first problem was that this embedding theorem does this K, which is not effective. It says that there's some power K, which defines it as an algebraic variety. But it doesn't tell us what is this K. And the first result, as far as I know, obtained in this direction was my collaboration with Hwang, 1999. And where we show that if this inequality holds, where rho x is the injectivity radius and m is some number, then kx tensor m plus 1 is very ample. So it gives an effective version of Kodaira theorem that it's enough to choose m as big as that this number gets smaller than sine square hyperbolic of the injectivity radius. Then with this M, you can embed this hyperbolic manifold as an algebraic variety. So that was the effective Kodaira embedding theorem. Now, after 10 years, what we are interested in is, okay, now we know that this hyperbolic manifold is an algebraic variety. So it's defined inside the projective space by zero set of algebraic equations. So the question is, what are these equations? So how to write it down explicitly as a common zero set of algebraic equations? So the question is, what is the ideal Ix defining the embedding? So that is the question. Now, this is much more complicated. So, because even for very simple variety, algebraic variety, to write down the equations defining this variety is very complicated, and there's no easy way. So, this is at the moment almost impossible that you can. I mean, I don't even try. It's quite a difficult job, but there are certain aspects of the ideal which can be captured more easily. And such aspects are sometimes more important than the explicit equations themselves. So let me define certain notions related to this defining equation, which are important. So this is rather standard for algebraic geometers, but perhaps not for complex or symplectic geometers. So let me recall this definition. So when L is very ample, on some projective algebraic variety, we say that L is normally generated or sometimes is equivalent to saying that satisfies N0 if this natural multiplication map is surjective for all k. So in other words, the ring is generated by just a section of L. So this is one condition of the line bundle, but it's a condition of the subvariety. So it's a condition on the ideal in some sense. And this is an important condition on the ideal. So studied much in algebraic geometry. And the second definition is that under the same assumption, so let's call this maybe 0. Right, 1. L is normally presented if the ideal Ix is generated by quadratic equation. in other words, you can define this x in terms of quadratic equations. Then it's called normally presented. And this sometimes is, instead of normally presented, we say that it satisfies N1. Now I'll define the next notion, but there's some generalization of these two notions into higher order. So now this is due to Mark Green. Generalize this. L satisfies NP. So this, I'm not going to give a definition of this because it's quite complicated. It gets more and more complicated as P increases. But also I cannot remember the definition. So the important thing is this means that the free resolution, the resolution of resolution of the ideal by free modules, free resolution of IX is of simplest form, simplest type to P step. So it roughly means that the ideal is of simple form up to certain order. So that's, but there's, which generalize these two notions. So this is N0 and this is N1, and then there's N2, N3, N4. P is not prime number, by the way. P is just integer. So for each natural number, there's a certain notion generalizing this. So if it gets bigger and bigger, the ideal looks simpler and simpler. Okay, so that's an important notion about the ideal. And even though we cannot write down the ideal itself explicitly, quite often we can say something about this property. These are called linear Syzygies properties. And they give good information about the equation. So the projective geometry of this variety. So these are important notions in algebraic geometry. Now our main result is relating injectivity radius to these concepts. So here's the main theorem today, which we proved last year. So now here X is projective hyperbolic, complex hyperbolic manifold, and if this is bigger than then KX tensor m plus 1 satisfies NP. So that is our result. So it gives an effective condition for the ideal to satisfy this NP property. And that, in other words, it tells us something about the defining equations in terms of the injectivity radius. Now this may look somewhat abstract to people not much experience with algebraic geometry, but this actually you can translate it into very explicit terms. So for example, so when the simplest case, when P equals 0 and M equals 1, this says that Kx second power of K is normally generated if sine hyperbolic square if the injectivity radius is big enough in this sense, then it's normally generated. And you can write it down more classically. So because the sections of Kx tensor M, this is classically called gamma automorphic forms. over 8 m. I mean, this is an object studied by like number theories. And so our result can be translated in this classical situation that the ring of gamma automorphic forms of even weights. So if you collect all automorphic forms of even weights, they form a ring, because if you multiply them, this again has even weight. Okay. So this ring is generated by automorphic forms of weight 2. So it suffices to just take the minimal one in the sense. So it has some, if this condition is satisfied, rho gamma. So, I mean, the injectivity radius is an invariant of this group, the discrete group gamma. So in terms of this discrete group, you can give a condition which guarantees that the automorphic forms of even weights are generated by forms of weight 2. So such result is explicit result. So it says that it's not a nonsensical statement. It gives some explicit information about the functions satisfying certain equations. Okay. Yeah, okay, so if you compare it, the very ample case, this was 2n over n plus 1 m, not this one. The condition for very ample case was just rho x is, then this is very ample. And in fact, this is weaker than this. It's elementary. You can check that this condition, if this condition holds, then it's always, this condition also always holds. Okay, so this is the main result. And now I like to explain the idea behind the proof of this. And but before explaining this, I need to explain the idea behind the very ample case, which in 1999, which is easier. So let me recall the idea behind the idea of the very ampleness, effective very ample. There are two ingredients. One is a soft ingredient, and the other is more hard ingredient. The soft part was a numerical condition for very ampleness. So you need a numerical condition for very ampleness. And as I said, numerical condition means condition on the cohomology level. So, and this is due to, this condition was due to Demailly, but it's originated from Syzygies. And it says the following. So if L is ample, X compact scalar, then if there exists some real number epsilon such that for all x, you consider the blow up of that point, with exceptional divisor Ex. Now if pi x star L minus 2n plus epsilon Ex Now this as a class in H11 of the blow up, if this is positive, then Kx tensor L is very ample. So it gives a condition in terms of the numerical information on the cohomology, which guarantees that this line bundle Kx tensor L is very ample. So this is a condition, numerical condition for very ampleness. So to prove our effective very ampleness theorem, we use this condition. And we check this for the hyperbolic manifold by the following inequality. So this in this old paper, we check this. For the hyperbolic manifold by the volume inequality. By the following volume inequality. And this volume inequality originated from Federer. So let's recall the definition. So BNR is the ball in CN with radius R. And here's the classical Federer inequality. It says that for any one-dimensional closed analytic subvariety, V in B and R, the following inequality holds. Volume of, this is volume with respect to Euclidean metric of the one-dimensional variety V is at least multiplicity of the variety at the origin times volume of the one-dimensional ball. That's the inequality. So let me draw the picture. So it says the following. You look at the following ball in CN. So this is B and R. And you take any subvariety, one-dimensional analytic subvariety, closed analytic subvariety inside the ball. So something like this. This is V. And what it says is that the volume of this guy, this V, is at least equal to the multiplicity of V. So there's a singular multiplicity at the origin. And times the volume of one-dimensional disk. So one-dimensional disk just means this one. So this is B1R. Is it the correct? No, B1R. Okay. So this is an optimal inequality where the minimum is achieved by this one-dimensional one. So it says that any analytic variety has volume at least equal to this one multiplied by this multiplicity at the point. And this is actually an inequality not on analytic variety but on minimal variety in the sense of Riemannian geometry. But analytic variety is minimal variety, so it satisfies this inequality. Now, we cannot apply this directly to check this numerical condition on very ampleness. So what we did is that So this is Federer's volume inequality. Now, what we proved in 99 is the same volume inequality, but not with respect to Cn, but with respect to the Bn1, the Bergman metric, the hyperbolic metric. So that was our result. That was the key point of our result. The same inequality holds if you replace the Euclidean metric by hyperbolic metric. So here, of course, Bn is bigger now. So this is Bn1. And here R is the hyperbolic radius. So you consider geodesic ball with respect to the hyperbolic metric, and then the same inequality holds. So that is our result in 99. And using this inequality together with this numerical condition, we can check the variampleness. So that was the proof. Now to generalize this to this case of NP property, we need two things. The first, we need some numerical condition for NP, this Syzygies condition. And then we probably need some generalization of this inequality. At the beginning, we had no idea what is the correct inequality. Now, this numerical part, this more soft part of finding numerical condition was actually already in the literature, although it's never written up explicitly. So, in this case, R is hyperbolic. Sorry, it's confusing. Yeah, it's confusing. So here, I have to change the notation. This R is hyperbolic radius. So actually, this is not one. This is unit hyperbolic ball, and BR here is the R with R can be bigger than 1, but this is a hyperbolic radius because B1 has infinite hyperbolic radius. Okay. Maybe later I will tell you. Okay, so now to generalize this to a higher order, so we need the numerical condition, so the idea of main theorem about NP. So first we need a numerical condition for NP. And this is, I should say, essentially due to already Mark Green. But somehow he wrote a wrong formulation. And then someone named Inamdar wrote a partial version of this. But then with the help of Rajasfeld, we figured it out correctly. So eventually this form is due to us. So it's somewhat complicated. It's not just one point blow up, because this ideal condition is rather involved. So here's the correct statement. So if you are not very, how do I say, much into algebraic geometry, you can just, you don't have to pay too much attention to here. It's some kind of numerical condition. But just to have the flavor, what kind of condition is needed. So this is, X is, again, compact scalar. And L is ample. And we need some more, one more technical assumption. The KX tensor L is NF. And this is sort of approximately mated by ample class. No, positive class. Nefness means that its cohomology class is in the closure of positive class. So these are the conditions we need. And then, let me see, I need some space. So instead of one point blow up, we need blowing up, simultaneous blow up of the diagonal. So we blow up the diagonal of x cross x. So here the diagonal, there's diagonal in x cross x, and we blow up this diagonal. And this is the exceptional divisor. And then there's projection, P, Q1, Q2. And this composition is called pi 1 and pi 2. And if this is positive for some, then KX tensor L satisfies NP. So that is the numerical condition. It's some geometrically complicated, but still the condition is numerical in the sense that it's positivity of a certain cohomology class. So if we check this, then it gives NP property. By the way, this is a sufficient condition. It's very far from necessary condition. So it's a very strong requirement. For very explicit variety, such criterion is not very useful. But for hyperbolic manifold, we have no idea about its algebraic geometry. So for such variety, even this can be useful, as you see. So this is the numerical condition for NP property. It's some complicated property about diagonal of the product of x. Okay. Now we want to check this using the injective radius. We want to check it for a certain range. That's the point. And to check such a positivity condition is usually, as in this case, is some kind of volume inequality. So we need to check some volume inequality. But this volume inequality is much more complicated than this one. This is very simple one. It's just a straightforward generalization of the classical Euclidean case, Federer's case. But now what we need is something more tricky. So here's the new volume inequality we need. So after 11 years, 2010, we checked this for Boole quotient by a new volume inequality. And this type of volume inequality is, I think, has not been studied in Riemannian geometry, or in other contexts. So this is something of interest. So let me give the statement. So here we are looking at the case of hyperbolic manifold. So we need to make some definition. So for each R less than the injectivity radius, we define the geodesic tubular neighborhood of diagonal by the following. This is WR. This is points on the hyperbolic manifold, pair of points whose distance is less than R. That is the definition of WR. So here the setting is we are looking at x cross x. And we have diagonal. And I'm looking at some tubular neighborhood of this diagonal. So this is WR. And the definition is that the radius, the distance between 2 points are less than R. So this is R. So I'm looking at this tubular neighborhood. Now, the volume inequality we need is the following. So this is a new volume. So for any one-dimensional closed analytic subvariety. So if you have an analytic subvariety inside here, like this, then this is now V. The volume of this guy is at least equal to, you take the, I have to explain this. So this is intersection of strict transform of V with E on the blow-up. So this is a one-dimensional variety with tilde. So you can define its intersection number with this exceptional divisor E. So that sort of plays the role of multiplicity along the diagonal. So this is, you can say that this is multiplicity of V along diagonal. So the volume of this guy, with respect to this product metric, this is product of hyperbolic matrix. Is at least equal to the multiplicity along the diagonal times this number. And this number has meaning. That this number is, there's a certain one-dimensional variety orthogonal to the diagonal. So there's which we call the anti-diagonal. But so there's some one-dimensional variety such that its volume with respect to the product metric is exactly 8 pi, exactly this number. So this number here is volume of this kind of the vertical diagonal, anti-diagonal, which is vertical to the diagonal, some Riemann surface orthogonal to this diagonal. So that's the analog of, some sort of analog of this Federer inequality in this situation, where the multiplicity at one point is now replaced by multiplicity along the diagonal, and the linear one-dimensional ball is now replaced by this anti-diagonal. So this is an optimal inequality in a tubular neighborhood of the diagonal volume. And if we use this, apply this inequality to this numerical criterion, then you get the main theorem. So the key point of our work is this inequality, actually. Of course, one difficulty, our initial difficulty was to figure out this inequality, that there was such inequality. Figuring out it was, in a sense, took more time. So once we figure out that such inequality must hold, then with some effort we could prove this. Now I will explain how one can prove inequality like such inequality. And for that I have to recall how one can prove this Federer inequality, the classical one. So here's the ideal proof. So I will just give very sketchy points. So how to prove? So the Federer type inequality. So Federer's original proof uses certain dilation of the variety, and that's more tricky in a sense. And especially if the metric is not flat, then it's more tricky. But there's a simpler way of doing it, realized by Lazarsfeld and so on. And this is by degeneration of Kähler potential. So by Kähler potential, I mean that you can write down the Kähler form on the hyperbolic metric by dd bar phi. So this phi, well, in this case, it was log 1 minus g square. So this is called Kähler potential. And to prove the Federer type inequality with respect to 1 point, in a neighborhood of 1 point, we degenerate this potential to introduce a pole. So modify phi to produce pole at the origin, and that is how the theory was proved. Then you can compare the volume with respect to Kähler form and the volume with respect to this degenerate Kähler form. And this comparison gives the volume inequality. That was the basic idea of the proof. Now we try to use this degeneration. So we want to degenerate the metric, now not at 1 point, but along the diagonal. So some analog of this. So that was our initial plan. Now there's a big difficulty in this case. So the main difficulty is on this WR, the Kähler form does not have Kähler potential. So in other words, you cannot write down the Kähler form as dd bar over one function on WR. The reason is that because you have this one-dimensional, higher dimensional variety, this diagonal inside R. So when you have a positive dimensional analytic variety, you cannot have Kähler potential by maximum principle. So there's no way you can write down the metric in this neighborhood as dd bar over one potential. And that's the main difference from the old case. So in the old case, it was just neighborhood over 1 point. So you can always write down the metric as dd bar over a potential function. But here you cannot do that. So that was our main difficulty. So how to, and in fact, this kind of difficulty is very common in several complex variables. That when you have a higher dimension, you don't have potential. That's the difficulty. So how to overcome this? It turns out that there's a very simple idea to avoid this difficulty. So this simple idea is that introducing the following. A function, a plurisubharmonic function, phi is a subpotential of a Kähler form omega if so instead of equality, you just require that it's inequality. So this is subpotential. Now, subpotential always exists. for any Kähler metric. 0. 0 is subpotential for all. So subpotential is something which is more abundant than Kähler potential function. On the other hand, since we are interested in lower bound of volume, we may use subpotential instead of potential. Because to measure volume is integrating Kähler form. But instead of this Kähler form, let's integrate this. It still gives, if we can prove lower bound with respect to this guy, then you get lower bound for omega. So to prove lower bound for volume, it's okay to use subpotential instead of potential. So that is how you avoid the difficulty. It looks very easy, but now the problem is the other one, how to choose this subpotential. Because if you choose like 0, it gives no result. So you need it, so the main problem is to choose good subpotential. And here there's no trick. I mean, you need to trial. What we did is some kind of trial and error. You modify the given potential function on the universal cover, because on the universal cover you do have a potential function. You try to modify it to make it survive on the quotient and still give us the subpotential. And just to impress you, let me write down the subpotential. I mean, in the sense that it's better not to try to do this by yourself. It takes some time. So let's define chi GW. This is tangent hyperbolic. And then Ft. This constant is some normalization. Then F dot chi is a good subpotential for omega x cosine. So this is essentially a function, a distance function, the function of distance. So this survives on the quotient, compact quotient. So this is a well-defined function on x cross x. And then we compose this function chi with this one variable function. And this gives the correct subpotential. So you can check that this satisfies this. This function really gives subpotential. And this function is also plurisubharmonic, which is non-trivial to check. So these are maybe good for students, exercise for students to check that this is a plurisubharmonic function. And this gives subpotential. And it turns out that this choice of subpotential gives the inequality that we need. And since this inequality is optimal inequality, at least for this problem, you cannot improve. You cannot find better subpotential. But we have no idea why this is exactly the best subpotential in this case. So somehow you are lucky that we tried a few and this somehow gives the optimal inequality. It's lucky, but it's really luck. I mean, there's no insight why such a function is the best choice. I'll stop here. Thank you.